Okay, let's say we have y squared plus x squared is equal to 4. How do we differentiate this? So initially what we did was we said that we needed it to be in this format. Okay, this is going to be 4 minus x squared. And then we said that we wanted it to be in this format, where we proceeded and said that this could actually use chain rule because we have a function nested inside another function. And so this one would give us what? Would give us negative 2x. And then inside here would maintain what we had, but then there's a half. Okay. And then we went on and said that this one now will give us 1 over square root of 4 minus x squared, if you follow all the steps. And then we can now go back here and say, what do we have here? We've got y, right? So we can say that dy over dx is going to be negative x, but then this is y, right? So we can say over y. That is how we differentiated earlier. And this is what all the methods we looked at used this method where you had to have y isolated and then x on the other side. So it was very explicit. Okay, but what happens if it's very difficult to do this? Very complex equations. What happens in that case? We can find a method where we can skip this step here. And then we can also skip, by doing that, we can also skip this step here. How do we achieve that? We achieve that by looking at these differently as separate functions. Instead of saying this can only be that, but we can look at these as separate functions. So we can look at these in two ways. We can say y squared plus x squared is equal to 4. We can look at this as a function of its variable. Okay, so this will be a function of y, this will be a function of x, this will be a function of, that will be a constant. So this will be a function of y, this will be a function of x, and this will be a constant like that. We can also look at this differently to say that we can look at this as a function of x, this one as a function of x, and this one as a function of x. This gives us the implicit method. Okay, let's look at these methods and then compare why we are actually preferring to go with this one. Okay, so we have y squared plus x squared is equal to 4. Okay, so we said that first we can look at this method here. Okay, that looks at each one of these as a function of its variable. So here we'll say 2y. But then because we dealt with this variable, the change will be in that variable. Okay, here, because we dealt with x, the change will be in x. And then this doesn't have any variable, so it's a constant rule there. Then we can go on and say y dy plus x dx is equal to 0. Okay, so now we can take this to the other side. We say y dy is equal to x dx, but negative. Okay, but negative. And then we can say x dy comes the other side, dx comes the other side, so it will be dy over dx. Okay, it's multiplication, so it becomes division the other side. This one goes the other side. It's multiplication here, it becomes division here. Okay, so we can see that we still get the solution that we got from the previous method. The problem with this method is that every term that you differentiate has to show the change, okay, in that variable. Now, if you've got a lot of variables, it becomes very, very cumbersome to do. So that's why now we go to the other method where we said every variable, okay, has to be treated as a function of x. Okay, every term has to be treated as a function of x. So what do we mean here? We mean that if this is a function of x, we're going to say 2y, okay, and then inside that function, we're also going to do this, okay, because we're assuming that this is a function of x. So the derivative has to be in terms of x here. Right. Then we go on and we say this one has to be treated also in terms of x. So it will be 2x, but this is x, a function of x. Okay. So we're going to have dx over x, like that. Then we're going to have 0 this side. Now, this is the same as 1, isn't it? Then this and this can clear out to divide 0 there. So we'll have y dy over dx plus x is equal to 0. Meaning that this can go the other side and this can go the other side. Meaning that dy over dx, this is addition here, so it will become negative here. This is multiplying, it becomes that. We still get the same solution. Okay, but we can still clean this up, because remember all this that we're doing, we said that we can use explicit if we can solve for y. Okay, where we can't solve for y, we go on and we say that we can treat individual, because we can't solve for one variable. Now we say that we can actually treat each of these independently, meaning that this will be implicit. Okay, it will be implicit. We can do for each one of these as implicit. But implicit, we can do it in two types. The first is where we treat each one of these as functions of that variable. But the best one is where we treat it as a function of x, each one as a function of x. Okay, so if we're going to treat each as a function of x, then we're going to have a situation where we have dy dx here, and then we have dx dx. But again, this disappears, right, at the end of the day. So what is the relevance of listing it in the first place? So when we are actually doing implicit differentiation, you will notice something like this. Okay, you'll notice something like this. You'll notice something like this, right? We can come and say we're differentiating this in terms of x. Okay, so this one will be 2y dy over dx. But when we see that we're differentiating an element of x, we can just differentiate without listing the dx over dx, which is going to be 0, like that. So it's becoming cleaner. We remove the 2's, we have dy over dx is equal to negative x. Then we can divide by dy over dx is equal to negative x over y. This way, we know where we're coming from. So we're not going to use explicit for these types. We're going to use implicit. Not just any implicit, we're going to use implicit where each term is treated as a function of x. So let's do some examples.